Welcome to this comprehensive deep dive into C# data types, a truly fundamental and essential concept for any aspiring programmer looking to build robust and efficient applications. Understanding these building blocks is the first step towards mastering C#. Understanding precisely how C# handles and stores different kinds of data is absolutely crucial for writing not only efficient but also error-free and maintainable code. This knowledge forms the bedrock of effective programming practices. Throughout this session, we'll thoroughly explore the core differences between value types and reference types, which is a key distinction in C#. Following that, we will delve into the practical applications and nuances of nullable types, providing a complete overview. Value types directly hold their actual data within their own memory allocation, much like a physical box containing its contents directly inside. This means the variable itself stores the value, not just a pointer to it, ensuring immediate access. Crucially, when you assign a value type variable to another, a completely independent copy of the actual data is made and stored in the new variable. Any subsequent changes to one variable will not affect the other, as they are distinct entities. Reference types, however, operate differently. They store only a reference or memory address to where the actual data resides in memory, much like a signpost pointing to a house's location. The variable itself doesn't contain the data, but rather its address. Consequently, assigning a reference type variable to another means both variables now point to the exact same data location in memory. This implies that any modifications made through one variable will be immediately reflected when accessed through the other, as they share the same underlying data. Let's now begin our detailed exploration with value types, which are foundational to C# programming. We will start our journey by examining integers, the most common type for whole numbers, and understand their various forms and uses. The int type is widely used for representing whole numbers, offering a substantial range from approximately -2 billion to +2 billion. This makes it a versatile choice for a vast majority of counting and indexing scenarios in your applications. Specifically, int is a 32-bit signed integer, meaning it can store both positive and negative values within its defined range. Its balanced capacity and performance make it a common and efficient choice for general-purpose counting and arithmetic operations. Moving on, we encounter float, which is designed to represent single-precision floating point numbers. This type is ideal for values that require decimal points, such as measurements or calculations involving fractions, where moderate precision is sufficient. Floats are 32-bit data types and typically offer about 6 to 9 decimal digits of precision, making them suitable for many scientific, engineering, and graphical calculations where extreme accuracy isn't the primary concern. They provide a good balance of range and memory usage. For situations demanding even higher precision, C# provides the double type, which stands for a double precision floating point number. This type is crucial when accuracy beyond what float can offer is absolutely necessary for your computations. Doubles are 64-bit and deliver an impressive 15 to 17 decimal digits of precision, making them the ideal choice for critical financial calculations, complex physics simulations, or any application where minute inaccuracies could lead to significant errors. Their extended precision comes at the cost of more memory. The decision to choose between float and double is a practical one, depending directly on your specific precision requirements for calculations and your application's memory considerations. Always select the type that best balances accuracy with resource efficiency for your particular use case. The bool type is wonderfully straightforward and represents a simple Boolean value, which can only be either true or false. This binary nature makes it incredibly powerful for decision-making processes within your code. Booleans are absolutely essential for implementing conditional logic, allowing your program to make decisions based on certain conditions, and for effectively controlling the flow of execution. They are the backbone of all decision-making structures like if statements and loops. Finally, among the basic value types, we have the char type, which is specifically designed to store a single Unicode character. This allows it to represent a vast array of characters from different languages and symbols worldwide. Characters in C# are always enclosed in single quotes, distinguishing them from strings. They can represent individual letters, numbers, punctuation marks, or various symbols, providing a versatile way to handle single textual elements. Now, let's smoothly transition and shift our focus to understanding reference types, which handle data storage differently than value types. We will begin this section by exploring strings, one of the most frequently used reference types in C# programming. The string type represents an ordered sequence of Unicode characters, forming text, and is undeniably one of the most commonly used and versatile data types in C# applications. It allows you to work with words, sentences, and any textual data. It's important to remember that, unlike value types, strings are fundamentally reference types. This means that string variables don't directly contain the text data. Instead, they hold a pointer or reference to where the actual text data is stored in memory. A key and often misunderstood characteristic of strings in C# is their inherent immutability. This means that once a string object has been created in memory, its content cannot be changed or altered directly. Therefore, when you appear to modify a string, for instance by concatenating or replacing characters, you are actually creating an entirely new string object in memory with the updated content. The original string object remains untouched and unchanged. Next in our exploration of reference types, let's look at arrays, which are powerful data structures. Arrays are essentially collections of elements that are all of the same specific type, stored contiguously in memory, providing an organized way to manage multiple related values. Just like strings, arrays are also reference types, meaning the array variable itself stores a reference to a contiguous block of memory where all its elements are actually stored. This contiguous allocation allows for efficient access to elements. You declare an array by first specifying the element type that it will hold, immediately followed by square brackets to indicate it's an array. For example, int declares an array of integers, preparing it to store multiple whole numbers. Crucially, elements within an array are accessed using a zero-based index, meaning the first element is at index 0, the second at index 1, and so on. This indexing system is fundamental for retrieving or modifying specific elements within the array structure. Finally, we arrive at objects, which are the fundamental building blocks and core concepts of object-oriented programming in C#. Objects encapsulate data and behavior, representing real-world entities or abstract concepts within your software. In C#, objects are essentially instances of classes, which themselves are user-defined reference types that serve as blueprints. A class defines the structure and behavior, while an object is a concrete realization of that blueprint in memory. When you create a new object using the new keyword, a reference to its newly allocated memory location on the heap is stored in your variable. This variable then acts as a handle to interact with that specific object instance. A powerful aspect of reference types is that multiple variables can reference the exact same object in memory. This allows for shared access and modification, meaning changes made through one variable will be visible through all other variables referencing that same object. Understanding the distinct roles of the stack and the heap in memory management is absolutely crucial for truly grasping how both value and reference types are stored and managed within a C# program. This distinction impacts performance and behavior. Value types typically reside on the stack, a region of memory known for its extremely fast allocation and deallocation processes. This efficiency makes value types ideal for small, frequently used data, as their life cycle is managed very quickly. Conversely, reference types are allocated on the heap, a more flexible memory region that allows for dynamic memory management and objects with longer lifespans. While offering greater flexibility, heap allocation comes with a slight performance overhead compared to the stack due to garbage collection. Finally, let's demystify nullable types, a powerful and incredibly useful feature introduced in C# that addresses a common programming challenge. They provide a safe and explicit way to handle the absence of a value for value types. By default, standard value types in C#, such as int or bool, cannot be assigned a null value, as they are designed to always hold a concrete value. Attempting to do so would result in a compilation error, enforcing their non-nullable nature. However, there are many real-world scenarios, particularly in areas like database interactions or parsing user input, where a value type might legitimately not have an assigned value. For example, a database column might allow null entries for an integer field. This is precisely where nullable types become indispensable, as they elegantly allow value types to hold a null value in addition to their regular range of values. They bridge the gap between value types and the concept of no value. You declare a nullable type by simply adding a question mark immediately after the type name, for example, int or bool. This concise syntax clearly indicates that the variable can now either hold a value of its underlying type or be null. To safely check if a nullable type currently holds an actual value, you can conveniently use its hasValue property. This property returns true if a value is present and false if the nullable type is null, preventing potential runtime errors. You can also access its underlying value directly using the value property, but it is absolutely critical to only do so after first checking hasValue. Failing to check hasValue when the type is null will result in an invalid operation exception at runtime. The null coalescing operator, denoted by, provides a highly concise and readable way to assign a default value to a variable if a nullable type is currently null. This operator simplifies conditional assignments significantly. For a practical example, consider int result equals nullable int 0. If nullable int is null, result will be assigned 0. Otherwise, result will take on nullable int s actual value. This provides a clean fallback mechanism. In summary, the fundamental distinction is that value types store their data directly in memory, providing immediate access and independent copies. In contrast, reference types store only pointers to data, allowing for shared access and more complex object structures. Furthermore, nullable types elegantly extend the capabilities of value types, enabling them to safely handle null values when the absence of data is a valid state. This feature is crucial for building robust and resilient applications that gracefully manage missing information. Mastering these diverse data types and understanding their underlying behaviors is truly a cornerstone of effective and efficient C# programming. This knowledge empowers you to make informed decisions about data storage and manipulation, leading to better code. We strongly encourage you to actively practice declaring, initializing, and manipulating all these different types in your own C# code editor. Hands-on experience is invaluable for solidifying your theoretical understanding and building practical skills. Don't hesitate to experiment with various scenarios, pushing the boundaries of what you've learned to truly solidify your understanding of how each data type behaves under different conditions. Active exploration is key to deep learning. Thank you for joining us on this comprehensive deep dive into C# data types. We hope this session has provided you with a clear and thorough understanding of these essential concepts. Now, go forth and keep coding with confidence.